Hello, my name is Mansour Shayegan. I'd like to thank you for your interest in our research. Before I take you for a tour, I would like to just give you an overview of the research we do in our lab. It involves fabrication and physics of low-dimensional semiconductor structures. And this involves a combination of three different fields. One is electrical engineering, one is material science, and one is physics, of course, which is what we are mostly interested in. Now, the physics, we are emphasizing the different phases of matter, exotic phases. I'll give you an example in a second. And to achieve these, we have to go to very low temperatures, use very high purity materials, and also use very high magnetic fields. So for the samples, we use gallium arsenide, aluminum gallium arsenide heterostructures grown by molecular beam epitaxy, and I invite you to also visit Lauren Pfeiffer's group, with whom we collaborate closely. Now, a typical sample has a gallium arsenide layer where the electrons are confined to, and the barrier material, aluminum gallium arsenide, is doped with silicon in this case. And the trick is that the electrons go from the donors into this well, and since they are far from the donors, they can move freely in the plane, long distances, and also they can interact among themselves. And that is what we are mostly interested in. The next slide here shows you some of the exotic phases that we are interested in. An extreme example is shown on the upper right picture. And there you see a Wigner crystal. This is essentially an ordered array of electrons. So the electrons like to form the structure to minimize the mutual Coulomb repulsion among themselves. There are many other states here that you can see: fractional quantum Hall effect, skermions, composite fermions. These are all essentially stabilized by this electron-electron interaction. It's a very rich field. 4 Nobel Prizes have been given in 4 different years in this field, and of course I hope that they will continue. So before my students tell you a bit about their experiments and the equipment inside the lab, I'm going to show you the inside of one of these pieces of equipment. This is a dilution refrigerator, which allows us to go to very low temperatures, and we put a big magnet at the bottom where we can go to, so that we can go to very high magnetic fields. So now my students will introduce you to some of the experiments.
Hi, my name is Ming. I'm a graduate student at the Shayegan lab. Behind me is a cryogen-free dilution refrigerator in our lab. It can reach temperatures as low as 35 millikelvin, and it contains a superconducting magnet with a maximum field of 14 Tesla. I've been studying the Wigner crystal phase in gallium arsenide 2-dimensional hole system using this equipment. As shown in this picture, the middle blue layer represents the 2D hole system, and the top and bottom layers represent the front and back electrical gates. We impose an AC excitation voltage to the bottom gate to set up an electric field E0 and monitor the electric field that penetrates through the 2D hole system to the front gate. This penetrating field depends on the screening efficiency of the 2D hole layer, and thus gives us information about its quantum phases.
Hi, I'm Kevin. I have been working with 2-dimensional electron systems confined to aluminum arsenide quantum wells for the past few years. Electrons confined to gallium arsenide quantum wells have a circular Fermi sea and are located at the center of the Broulan zone. In contrast, in 2-dimensional aluminum arsenide systems, electrons occupy conduction band minima at positions away from the center of the Broulan zone. These are known as valleys and have an anisotropic Fermi sea and an anisotropic effective mass. The aluminum arsenide systems have unique capabilities, like the possibility to control the density of electrons in each valley with a piezoelectric actuator at cryogenic temperatures as low as a few tenths of millikelvin. Recently, advances in the growth of aluminum arsenide systems has allowed us to fabricate systems of extremely high quality. In such systems, we find, with the aid of very low temperatures and strong magnetic fields, that the Coulomb repulsion energy dominates relative to other energies of the system. Regarding the physics of this system, we have studied the phase diagrams of electrons making transitions from solids to liquids, and the spontaneous spin polarization of electrons at very low densities.
Well, I hope that you have enjoyed this short tour, and I hope that we can visit in person one day. And meanwhile, if you have any questions, please drop me an email. Thank you.